This is the Pearson Edexcel FP1 sample paper for starting in 2017. Based on this book here, let's go straight into it because it's going to be a long one. Simpsons rule, this should be 5 guaranteed free marks. You draw a table with 7 spaces because it's 6 intervals. You start at 1, end at 4, and then you just fill in the spaces with whatever gets you to 1 to 4 in a nice even way. So the interval here is length a half. Nice. And then we just substitute 1 into here and 1.5 into here and so on into the function of root 1 plus x cubed, and we get all of our y values, which are all of these. I left them as roots just because it was easier for me to type that way. You can write them all as actual decimals if you want to. And then Simpsons rule, you can just use this. You don't need to do anything intelligent. It's 1/3. The length of the interval is a half here. That's h. The ends, I'm saying this one and this one. Those y values are the ends. The odds are the first, the third, and the fifth of the actual values that aren't endpoints. The first, the third, and the fifth, those are the odds. And then plus 2 lots of the evens are 3 and root 28. So hopefully that's more clear if I do this. H has become a half because that's that. The endpoints are this one and this one. So they're there. 4 times the odds are 4 times this, this, and this added together, and then 2 lots of this and this added together. Just type that into a calculator and you get 5 excellent marks. Good question number 2. So it's Leibniz's theorem, sorry. So f of x we'll say is this, g of x we'll say is that. We have to show dny by dxn, which would usually be quite hard, but these two things are quite easy to differentiate, so it goes okay. The first differential is 3x squared, the second is 6x, the third is 6, and then of course everything after that is 0. This one's nice and easy as well. You just bring the k down, that's the first derivative. Second one, you do it again to make a k squared, and third one is k to the 3, and so on, and so we just get this result in the end as well, which is quite useful. And now show this thing here. Now, according to this theorem here, dny by dxn is going to be equal to this one times this one, so the first from this list and the last from this one, plus n choose 1 of second from this list, second to last from the list before, so the n minus 1th derivative, and then plus n choose 2 of this one times the one above that, and then you keep kind of, it's a bit like binomial theorem, isn't it? Keep kind of going up, down one list to go up the other one with the n chooses all in the middle. This should really be an n choose 0 here, but it doesn't really matter. Of course, I can't actually do this all the way to here. Well, I can, but loads of these are just going to be 0, aren't they? Like, I only need to do this up to f3, so I think this is going to be the whole thing. So we have f and g n, so that's the first and last, then this one and the one before it, so first here, second to last here, and then f2, and then the one before that in the g's, and then just n choose 1, n choose 2, n choose 3, and then everything after that is 0 because f derived 4 times and further is just 0 every time. So we end up with this. Now we can substitute some stuff in here, so I think I've just substituted in all of these things that I've got here, and I think we get this. Now n choose 2 and n choose 3, the way that we can write that is to do n factorial over 2 factorial, n minus 2 factorial, and likewise here. N factorial over 3 factorial, n minus 3 factorial. And now what we can say here is, this here is n times n minus 1 times n minus 2 times n minus 3 and so on. But that just means that's n times n minus 1 times n minus 2 factorial. So basically all of this cancels all this except for the n and the n minus 1. And likewise, same thing here except for the n minus 1 and n minus 2. So I think we just end up with this. 2 factorial is 2, 3 factorial is 6. Those two things will cancel. I've also factorized out a kn minus 3, which leaves 3 of them here because those things added make this. Leaves 2 of them there because those things added make this, and so on. I've also factorized out an e to the kx because that's just in every single term. I did this, of course, because it told me to. I'm always looking at the thing that I'm aiming for. And we can, of course, simplify this. That makes a 3, that makes a 1. Don't need this 1 there anymore. So, and I think this is exactly right, except I've written the letters in a different order, which is probably fine. And we're done. Good. Question number 3. We have a differential equation here, second order, that we need to turn into a nicer one. So we use this transformation. Of course, I can just derive both sides with respect to t. Now, this is a function of t, this v here. So this is a product. So I do, when I differentiate with respect to t, I differentiate this one, which becomes a 1, leave this one alone, and then leave this one alone, and then derive this, which becomes dv by dt. Now we also want to differentiate this again, so let's differentiate both these, and I've tried to make this nice and clear. Differentiate this side with respect to t, differentiate that side with respect to t. When you differentiate this, you just get d2x by dt squared. When you derive this, it's kind of similar. V first is just dv by dt, and this is a product. In fact, it's the same product almost that we were differentiating earlier. Differentiate the t, and we just get 1, and leave this one alone, and then leave this one alone, differentiate this for that, and I think that will be that. And we can, of course, substitute that into there, We can put this into there. And I think I just left everything else alone, did I? Yeah, I literally just left... Oh, and then I just replaced this x with a TV, of course, from here. I think everything else I've just left alone. Expand everything out, and I think we get this. And then, of course, what's quite nice here is that this one cancels with this one cancels with this one, and we're just left with this, I think. Those are the only terms that are left. And then we divide by t cubed, and we get the answer that we wanted, which is good. Hence, find the general solution for C. So this just becomes a core pure maths question now, I think, pretty much. So the auxiliary equation of this is just, let's say, w squared plus 1 equals 0. That, of course, has roots w are plus or minus 1. We're missing the w term because there's no dv by dt here. And there's just 1v, which is where that comes from, just to be clear. The solutions to this are of this form, aren't they? When you just have imaginary roots, there's no real bit. It's just going to be this. There's no e to the bit because there's no real bit. Technically, it's e to the 0, which just makes it 1, so that's just why that's not there. We have this, and then we deal with this bit here, because this isn't just a 0. So we just say v equals maybe mu t or lambda t, or really whatever you want, kt, you could have used anything really. Derive that to get this, derive it again to get this, and then put those three results into here, and we just get that mu must be 1. And therefore, this is the complementary function with just a 1 there. Sorry, that's the particular integral with just a 1 there. That's the complementary function. Put them together and we get our general solution in V. Except we didn't really want a general solution in V. We wanted a general solution for the displacement. You know, I've solved for V here because, of course, the differential equation was in terms of V. But I want it in terms of displacement, which is what x is defined to be. So, okay, we just replace this. We say V equals x over t, and we put that in there. And then we can, of course, times everything by t, and we get our general equation for the displacement of c, which is x in terms of t, and that's good. State what happens to the displacement as t becomes large. There's only 2 marks here, so we know that there's not any real maths needs to be done here. When t is very large, these two things are just going to wobble around. But even if they both happen to be negative at the same time, when t is large, this counteracts them anyway, and we just get a very large number in this bracket, times another very large number, both of which are positive. So we just get a very large positive number. Now x is the distance from the center of the spring to the fixed point, and so what this is saying is when t is very large, the distance from the center of the spring to this fixed point is just getting bigger and bigger and bigger, which doesn't really make any sense. Like this spring would snap eventually. It's just not really how a spring works. So yeah, I would just say something to that effect. You could even substitute a number in or a couple of numbers here just to prove your point, but I don't think you really have to. Anyway, question number 4. So another differential equation then. Just take this original thing here and just start deriving. So this derived is just, you put 3's here. This is a product, so derive this term first for just from -2, leave this one alone, and then leave this one alone and derive this one, which gets you this, and then y derived is dy by dx, and just keep going. Differentiate again. So this becomes 4's, this becomes 2's, and there's no product here. Well, there is, but it doesn't really matter. Oh, of course, actually, I can notice, just to save me some work, I can put those two things together, can't I? And then I can start deriving again. So that becomes that. There's no product here anymore, so that just becomes that. This derive the x goes away there, leave that alone, leave this alone, derive that. And do it again. You can tidy up actually these 2 bits first again, and then you can differentiate again. These becomes 5's, these become 3's. There's a product here, this goes away, leave that alone, leave this alone, differentiate that, and you get this. Move those to the other side. These 2 things go together as well. Then move them to the other side, and I think we get this. So A is 2 and B is 5, it looks like. Good, 4 marks. Hence find a series solution in terms of this. So we take these initial conditions, y is 0, x is 0, dy by dx is 1, and we essentially shove them into here. I'm just going to put all the results we found. All of my results aren't very helpful to me. Well, they are very helpful, but all I'm going to do here, just to get to these, is just to rearrange. So look for this one, and this one, and just make sure I've just rearranged them to have this thing equals something. That's just going to be more useful to me. Now look at this one. We can also rearrange that if we want to. But I'll just do it in our heads. It's 2x dy by dx minus y is this. So 2 times x is 0, times this is 1, minus y, but y is 0 as well. It means that this is also 0. So our first one is 0. Then the second one, we can use this result and just plug in any relevant numbers. So this is 1, this is 2, obviously. This is 0, so this just is going to go away. This is also 0, so it double goes away, and we get 1. The next one, using this one here, we have 3 times 1. No, we don't. We have 3 times 0, this one's 0, sorry, plus 2 times 0, so this is all just going to be 0, cool. And the next one after that, we're going to have 2 times 0 times 0, that all goes away, plus 5 times here is 1, so that becomes 5. And this is quite nice because then when I'm just lining up those, when we use the Taylor kind of series-like thing that this is, we just have, we have the x squared over 2 factorial, 3 squared over 3 cubed over 3 factorial, and so on. And we just have all these evaluations here. Don't know why there's 2 positives there. Mistype, that's okay. I guess it's technically completely correct, so that's fine. And we have this is equal to 1, so we have one of those. This is equal to 0, so that just goes away. We have one of those. We have 0 of these. We have one of those, 3 factorial over 3 factorial. And then we have 0 of these, and we have 5 of those over 5 factorial. 5 over 5 factorial is just 1 over 4 factorial. 4 factorial is 24, and we'll get an answer that looks a bit like this. And good, let's go to question number 5 then. This is quite an interesting question, I think. It's about a parabola which we can draw like this. Got a point P there, got a point Q there. I've drawn these in very specific places such that the picture looks at least a little bit like it should do. So the line O to P, there is a line, there's a normal to P, sorry, so this is a right angle here. There's a normal to P that just happens to pass through Q. That's why I've drawn it like this. And then you've got some lines O to P, O is obviously the origin, so O to P and Q to P, and they also meet at right angles. They're also perpendicular to each other. And we're just being asked to, given that this is the setup, prove that P squared is equal to 2. First, we're obviously going to start by differentiating this thing. So do some implicit differentiation there, and we get this. We can rearrange that, of course, to make this. And so the gradient of the curve at P, by just putting in this value into here, is 2a over 2ap, which is just 1 over p. And therefore the gradient of the normal is going to be minus p, because minus p times 1 over p is minus 1. So this line here has gradient minus p. It also goes through this point, so I can just do y minus y1 equals m, which is this, into x minus x1. I can do some sorting out here. In fact, what have I done there? I've also put in the other coordinate that I know that it goes through, so that's y1 and x1, but I also know that it goes through there, so I've also put in those coordinates because the line goes through both of these. And I think after a bit of work, this of course becomes q minus p into q plus p, cancel a bunch of stuff out, and we get this. Now I'm going to leave that there for a little bit, but that seems like it might be quite helpful later. We next look at maybe these lines here. So this line has gradient clearly just because it goes through the origin. Rise is this over run is that. And it goes through the origin, so c is 0. So this is just the equation of this line. And likewise, this one is just going to be this. Again, just doing rise over run stuff. So we have this. I'm just checking whether I should have put a negative here, but I think I'm good because I'm essentially doing 0 minus this over 0 minus that, aren't I? And then I can just cancel out the two negatives, and I think I'm going to get this anyway, so I think this is fine. Cool, so now what we can do is you can say, well, this gradient times this gradient, because they're also perpendicular, must be equal to minus 1. Now a bunch of stuff cancels here. We get this, which we can times by, we can bring this 4 over and we get this. And now when we expand out this, we get that. But if PQ is equal to minus 4, minus 4 is 4, and I think we get P squared. 4 minus 2 is 2, so P squared must be 2 based on this. And I think that's good to go. That was quite a nice question. Question number 6 is a vectors question. So we've got a plane that goes through this point, this point, and this point. We're looking for the Cartesian equation. Now the easiest way to do this is to find the vector a to b, which is just how many do you have to get from a to b, which is this, minus 1 every single one. So therefore it would have been maybe easier on the next bit to go b to a, but it doesn't matter. Then a to c is this. And now for a Cartesian equation of the plane, I'm going to try to aim for the r dot n equals k formula, because r dot n equals k is essentially Cartesian form, just written with vectors, because of course the r becomes an x, y, z, then you dot it and you get Cartesian form. And the n is the normal vector to the plane. So I want a normal vector to this, to the plane here. Now how do I get a normal vector? Well, actually the definition of cross producting two vectors is a vector that is normal to both. So if I have this vector AB which lives in the plane and this vector AC that lives in the plane, if I cross them together, I get a vector that's normal to both of those two things, therefore normal to the plane. So we cross the two vectors together. I won't go through this in very much detail. using 1, 1 would have been easier, but it doesn't matter. You get this, and so that vector is normal to the plane, which means I can use this form here with the n being this vector, and now I can just, to find out k, I can just put any of the points that I want. Probably would have been easiest to use 0, 1, 0 to be honest, but I didn't think that far ahead. I just put in this point into here, dot them out, and you get k is 1, which of course you can just see if you put 0, 1, 0 in. You just get 1 from the middle bits. And then we put k as 1 in there, and we end up with this. And like I said, r is just x, y, z, so this becomes minus 3x plus y plus 2z equals 1, and that's the equation of that plane in Cartesian form. Find the volume of the tetrahedron. You can draw some pictures and do something intelligent here, or you can just, I think I did that in the 2020 paper, or you can just use the formula. A to d is this, just again, you need 9 in that way, you need 3 in that way, you need 4 in that way. And the volume of tetrahedron is 1/6 of AD dot AB cross AC. And then you can do the modulus here just because if it's negative, you just make it positive. It's worth mentioning you could swap the order of some of these as long as you do the cross first and then dot it, of course. So okay, we do this, cross those two together, and so we actually already crossed those two together. It makes this, right? We just did that, so that's fine. Now we can dot them together, we get this. And then we can, of course, just simplify down and we get this here, which is good. Of course, that is actually negative, which is why I needed those moduluses in there to make it positive. The plane has equation. This is a new plane that we're looking at, a different plane, different one to this one. And the point E lies on AC, right? So E, I mean, the line AC, this is some interesting notation that I came up with while watching a Los Angeles Clippers game last night. The line AC is this point plus lambda, the amount from A to C, which we already worked out. And so if E is just some point on this line, I can just say E is of the form this. Its x coordinate is 1 plus lambda, its y is 2 minus lambda, and z 1 plus 2 lambda. And I can do the same for F, right? Like F lies on AD. AD is just going to be A plus mu maybe amounts of this vector, and I can define F to be this in exactly the same way. Now E is on this plane here. So if E's x coordinate is this, its y coordinate is that, and its z coordinate is that, I can just shove those three things into here. In fact, there's no z to put in, but I can put the other two into here, and I can solve for lambda, and I get lambda as a fifth. So therefore, I can know exactly where E is. I just put lambda as a fifth, or 0.2, into here, and I get E as that. And exactly the same for F, right? F has x coordinate that, y coordinate that, z coordinate that. Put those three things into here. You get this, solve for mu, you get mu is that, and then put mu into here, and you get F is this coordinate here. So that's just some work I can do. I actually don't have to do this, because, and you'll see why, but it's cool that I did. A to E is therefore this to this is going to be 0.2 in the x's, minus 0.2 in the y's, and 0.4 in the z's, so that's going to be A to E. And A to C we already knew is that, so I'll just write it out again. And I think if I just times this by 5, I'll get that. So therefore, if I divide this by 5, I'll get that, and k must be a fifth, which I don't think I ever wrote down anywhere clearly. Maybe I should just write here k is equal to a fifth. Given that this is this, now we can verify that my math is good now, because A to F is, from here to here is 1, from here to here is 1/3, and from here to here is 4/9. If I times 1, 1/3, and 1/9 by 4/9 by 9, I think I get 9, 3, and 4. So that's perfect. I think I've got this right, hopefully. Show the volume tetrahedron of this is 45 times what yeah, you can read. Okay, so the volume of ABEF is going to be a sixth, A to F, across these two things, exactly the same way that we did the volume of this one. Now, A to F we've been told is a ninth A to D. We've also shown it, which is nice. So that's a ninth A to D. A to E we've also shown is a fifth A to C. And these numbers here, you can just bring those straight out, and you don't need to prove why. You don't need to do anything intelligent here. It's only 2 marks. Just take this 1/9 and this fifth out to make a 45th of this thing here, and this thing here is exactly what we described earlier, the volume of ABCD, and therefore it's 45 times the old one. And, or sorry, the old one is 45 times, no, yeah, the new one is a 45th of the old one. This one times 45 would make this one. I'm just so confused. I don't know what's going on in my head. You can read, it's fine. I don't know what's going on, really confused. I'm very tired. P and Q have an ellipse, this thing here. So that's, I mean, firstly, as soon as I read ellipse, I just go to my cheat sheet. And then I divide all this by 4 because I want a 1 here according to the sheet. This is in the formula book, by the way. So A is 2 and B is 1. And forever no more in this question we'll be using this. Now, I think the reason that I found this question quite hard, I'll say this while I'm just drawing the picture that we've got here, is because I think this is, usually I can plan out a question quite well before I even do it, but this question I was feeling around in the dark very much so, a bit like a step question. I wasn't really sure how to make progress at points and how to plan out the whole thing. And I think you guys may have felt the same way. We've got tangents to these points, which meet at RS, and what we're being asked for is the equation of this line, and to show that it's this thing in terms of RS. So okay, I mean, the first thing we have to do is differentiate this, right? We have to differentiate this, rearrange for dy by dx, and therefore we can find the gradient at this point by putting in this y coordinate and this x coordinate, like so. By the way, I've defined these as these coordinates because that's what this means, right? And I put a theta here because for some theta it might be there, and for some beta it might be down here. So just to explain where those come from, it's just this bit here. So anyway, we put those in, and therefore the equation of the line, the blue line I'm talking about right now, because of course that's tangent to this curve here, so therefore has gradient this, it's going to be y minus this into m, which is this, x minus that. And I times by 4 sine theta here, and when you add 4 sine squareds to both sides, you get 4 cos squared plus sine squared. Cos squared plus sine squared is 1, so you just get a plus 4. And then I divided everything by 2 to get this. Now you can do exactly the same over here, and when I say exactly the same, I mean literally exactly the same. I just copy-pasted everything and replaced everything with betas, and you get exactly the same thing here. Now, this is the point where I really stalled and didn't really know what I was doing. But what you can say is, okay, the information they've given you is about RS, which is the meeting point of those two lines. So let's think about where this line, which is the equation of this one, and this, which is the equation of this one, let's think about where they meet. Now, how would we do that? Well, we could rearrange for y and set them equal, but that's way too much work. Let's just rearrange for 2. There's a 2 both here, so let's just move this x cos over to this side and this x cos over to this side, and say, well, this plus x cos equals 2, this plus x cos equals 2, and since they both equal 2, we can just set those equal to each other. So that's that. And now I know the solution to this is at RS. X is R, Y is S. So I'll put that in, and it just seems natural to get the R's and the S's on equal side, on their own side. So I did this, and then I just parked that there for a second. Now, what else do I need to do? Well, the question is actually about L. So how do we go about finding L? Well, the gradient of L is going to be sine theta, is rise, which is sine theta minus sine beta, over run, which is 2 cos theta minus 2 cos beta. So that's the gradient of that. And again, we can think about y minus y1 equals mx minus x1 if we want to, by using this as our y1 and x1. So I think that's what I did next. Except, actually, just before I do that, notice how this is where this comes in, right? Because if I just divide both sides by cos minus cos, and 2s, I think I get this, which is very helpful because this is almost this. There's two things to fix. Firstly, I need a denominator of 2, lots of this. So let's just times both denominators by 2. And also, I need these to be the other way around. So let's times both numerators by minus 1. And then I think I get exactly what I need. So when I'm doing y minus y1 equals mx minus x1, I can use this as my m, which is perfect because that's what's going to give me R's and S's in the thing down here. So okay, expand this out, I guess, and now this is almost perfect, right? Add Rx to both sides, and we have all of this perfect. It's just this which is out. And I've still left this here, because this, you can go back if you need to, but this was the equation of this line. So, but I know this line goes through Rs, so I can just put X's R and Y as S in here, and I get this. And if I add that to both sides, I get this, double it, I get this, and so therefore that's equal to 4, which is this, so therefore that's equal to 4, and I've shown what I need to show. It's possible to just do this by writing x1s and y1s and x2s and y2s, but I wanted to do it using this form here because that's what you more usually do in these questions. Like that's usually, somehow usually those things sort of cancel out, and it's much more helpful. So that's why I just wanted to continue doing it in the same way that we've done previous questions like that. So it is possible to simplify this a bit down and not have to deal with these thetas and betas, but it's all the same idea. Even if you do, everything just works out the same and you do the same kind of thing. Question number 8 is just a terrifying question to look at because there's so much reading to do. But let's just ignore this first and just think, okay, well, we've got a function here. I don't even need to see this graph. I don't care. Got a function here in terms of x. And we're going to show this thing where t is that. Now, okay, first thing, this is not the usual t substitution. The usual t substitution is that, which leads to usual results of these two things. Now, if x has become x over 4, that's almost like we're using x over 2 in here. X over 2 is x over 4, which means we can just replace these with x over 2's, and we get corresponding results for this substitution here. So, okay, that's fine. Now, if I wanted to substitute those, I could find sine of x by doing a double angle formula, and I can substitute those things into there. The problem with that is that I then have h in terms of t, and then doing dh by dx would be annoying. I'd have to use some chain rule because I'd already have it in terms of t. So I think the best thing to do would be to differentiate this first because it's already in terms of x right now, and then substitute in all of the t's. Rather than doing some chain rule. So differentiate first, we just get this. I'm not going to go through that too carefully. Now I have cos x over 2, I have sine of x over 2, don't have cos x. So how do we find it? Well, the formula book doesn't give us this, but it does give us cos of a plus b is equal to, I mean, you just set a equal to b and you get this quite quickly. So okay, that means that cos of x is equal to cos squared of x over 2 minus sine squared of x over 2, just replacing 2x with x. And therefore we can say this is cos x equals cos squared x over 2, which is this, minus sine squared x over 2, which is that. And this just becomes 1 minus 2t squared plus t to the 4, and then minus 4t squared makes, I think, this. I can put those two things together as well. Not going to bother squaring out the denominator yet. I can just put these all in here. So putting this result, and this result into here, I think is what I've done there. And now, like I said, I can put those things together. I can also, what I've done here is I'm aiming for the same denominator everywhere, right? So I'm writing this 15 as 30 over 2, just to make a 2 on the denominator. I'm going to times these two both by 1 plus t squared on the top and bottom, here and here. And then I think the denominator is the same for all of them. So I think now I can bring them together. This is just some algebra that you just need to do. I'm not too worried about this factorization, and I'll explain why when we get to it. So I'm not going to try and do anything intelligent here. I'm just expanding out. I'm just going to collect everything together. Collect all of that, you get this. And now here's the reason I'm not worried about this factorization. Because if they give you the answer, you can just do a jottings down here and you can say, oh, I wonder what happens if I expand this out. Well, you get this, and then that is that. And therefore this thing will factorize into this thing. So I can just factorize like that, and I'll get all 6 marks for that. So that's good. So sometimes if they give you the answer, you do not need to worry about being intelligent and factorizing early. Just expand out, just collect everything together, and then use their answer, work backwards, and you should get to yours. As long as it matches, of course, which you just pray that it does. Okay, so the next bit of the question then is they give you this, which is about the height of the tide at some time of day. So we've got these peaks. You notice that this graph is very similar to this graph, right? Goes up, wibbles a bit, goes up, and so on. So that's kind of interesting. It says, yes, blah, blah, blah. So this is probably going to be a model for that then, is probably what we're going to say. We have the equation, we know lots of things about this model. We're probably going to use these equations here to do something with this. Suggest a value of k such that this could be predicted using kh of x. Now, k, of course, stretches out the graph vertically if you just put that in front of a function. So we look at this and we go, okay, well, when x is 0, that looks like 70. Let's just double check. When x is 0, what happens? Yeah, it's 70. So we go from 70. Now this looks like 1.5. So we're looking to squash our graph down from 70 to 1.5. So we'll just say 70 times something needs to equal 1.5. 1.5 is 3 over 2, so that's going to be 3 over 140. So I think this squash we'll get this starting point down to this one, and that seems like a reasonable thing to do. Why may the model be suitable to predict the times of peak tide or high tide, but not the height themselves? Well, it's suitable for the timings because you can see that this is periodic at roughly the same rate as this is. I'll mention this later, but you notice that this is 40 hours across because there's a whole day from here to here. Plus 4 is 28, plus another 12 is 40, and this is also 40 across. And you can see the first peak is just after here, and the last peak is just before it. So the peaks seem to line up, so it's probably pretty suitable for estimating when the peaks happen. But the problem with the heights is that our model, of course, just does the same thing over and over again, right? It peaks at the same time every single time, whereas this kind of fluctuates a bit more. So it's probably good for the times that the peaks happen, but it's not so good for predicting where those peaks are, because these seem to be very random, whereas these are just very uniform. And so yeah, so just say something to that effect. Now the last 6 marks is using the result in part A, which is this. Estimate the time of high tide on the 4th of January. So the high tide 4th of January, so high tide in here is clearly that one. So okay, we need to find we need to find this one here. Sorry, highest tide height. Yeah, so that's why it's not this one, isn't it? The highest tide height. This is clearly a little bit higher than that one. So highest tide height on the 4th of January. So we are looking for this one here. So okay, we're probably looking for this peak here then, via thing. So we need an x value between 25 and 30, probably about 26 or something like that. So how do we get that? Well, of course, this thing is going to peak, or really this thing is going to peak when dh by dx is 0, right? That's when the graph is stationary, dx by dh is 0. So we set this equal to 0, but of course we don't need the denominator, we just want the numerator to be 0. And this is why they put it in factored form, why they gave you factored form, isn't it? Because now we can just say, well, either this needs to be 0 or this does, and we get those two, or those 4 solutions, I should say. Now, how on earth do you know which one to use? Because of course these are in terms of t. I would like a terms of x value, right? I want to know the x value for which this is a peak here. Because of course if I knew the x value, like I already said, this is 40 across, this is 40 across. So if I knew the x value, I could just add 8 hours to it essentially, and I'd get the time when this peak happens. So I need the x value, I don't need t values. So that's when I go back to the substitution, and what I originally did was I said, okay, well, I don't know which 4 of these solutions it's going to be, so let's just try one of them. Let's just try this. Do tan inverse. And now, of course, when you do tan inverse of a number, you get the principal solution from the calculator, but of course, tan runs from, I haven't put the graph, I should have put the graph down here, shouldn't I? But I'm using this space later. Tan is periodic every pi. So the principal solution is here, tan inverse of this, but you could also just add pi to that, you could add 2 pi to it, and you'd get any of these 3 solutions. Now, x is between 0 and 40, of course, so I don't care about going backwards pi places, and I also don't care about going too far forwards, because when I times all these by 4, which I'm eventually going to do, I notice after the 3rd one I'm going to be too far. So okay, so we just need these, I just want to write these 3 down. Now the problem is that 6 refers to probably this one, that minimum point, 18 refers to maybe this one, and 31 refers to this one. Notice how we're always on this bit here. So it seems like this t solution of 3 plus root 26 refers to these peaks, which are the wrong peaks. I don't want those. I want these peaks. So I've got 3 other t's to go with. Which one is going to cause these peaks? And of course, you could just do trial and error. You might have enough time. It doesn't take very long after you practice doing all this once. It doesn't take long to just try some more things. But what I decided was, well, okay, 3 plus root 26 is, I think, the second smallest positive value of these ones. The smallest positive value is minus 2 plus root 31 over 9. That's the smallest positive. So it stands to reason, because t is an increasing function, that if I use the smallest positive t answer, when I do tan inverse, I'll get the smallest principal solution for x, which I hope is going to be this one. And that's exactly what happens, right? So we do tan inverse of this, we get this, we can add pi, we can add 2 pi, we can times all those by 4, and we'll get these 3 solutions. And I think 26.64 looks bang on this one. So I'm happy with that. I think that's the x that I'm looking for. And of course, x is 26.64, we want to be 26.64 hours beyond 8 o'clock then. Now, 24 hours beyond 8 o'clock is clearly this 8 o'clock. So we need to go another 2 hours, which takes us to 10 o'clock. And then 64.64 is, of course, not 64 minutes, because that doesn't exist. We do 0.64 times 60. I should have put this 40 hours thing in earlier, because I've talked about it a couple of times, but it doesn't matter. 0.64 times 60 is going to be this. So it's going to be 8 plus 24 is this, plus 2 is 10. So it's going to be 10.38. I think if you actually use a proper value here rather than rounding it, this goes to 39, or 38.5, which rounds to 39, but you're allowed 1038, 1039, or 1040. So there's a bit of space for rounding, because this is quite a long question. You had a lot to do. But that's the whole thing, and thank you so much for watching, and I'll see you next time.